A very good day to Dr. Haisham. We are from Group 3, Section 4. Our project title is Electric Field Analysis of 11 kilovolts 3-core XLPE cable termination in switchgear using FEMM. I will be explaining for the introductions. As we all know that 11 kilovolt 3-core XLPE insulated cables commonly used in medium voltage distributions, which is in urban and also industrial zones. It is preferred due to its compactness, thermal stability, and also environmental resistance. For the importance of proper termination interfaces critical in ensuring cable longevity and also system reliability. However, improper design may cause electric field concentrations, leading to partial discharge and also insulation degradation or failure. The challenges in three-core cable termination is confined spans in medium voltage switchgear panels, mutual interaction between cores complicates stress control, and also stress points at metallic glands interfaces and also core ends. The role of simulation that we are going to use is the FEMM software, which is the finite element method magnetics, to help us to visualize field distribution and also support insulation design improvement. Therefore, for our project goals, we would like to develop a simulation model of 11 kilovolts 3-core XLPE cable termination using FEMM, and also to investigate the electric field distribution and identify potential high-stress regions at the interface with switchgear. Lastly, is to propose termination design recommendations for improved dielectric stress control and also the insulation performance.
Okay, next is I will explain about methodology for the material setup of the cable. Okay, the structure of a three-core XLPE insulated cable layer by layer. At the center is the copper conductor which carry the electric current and has a size up to 5.5 millimeter in radius. Around the conductor is the conductor screen, a thin semiconductive layer from 5.5 millimeter to 6 millimeter that help spread the electric field evenly. Next is the SLPE insulation layer, which is the main part that insulate the cable stretching from 6 millimeter to 11.5 millimeter. On the top of the that is another insulation screen from 11.5 millimeter to 12 millimeter, also semi-conductive to further control the electric field. After that, the lead sheet from 30 millimeter radius protect the cable from moisture and damage. The last layer is the PVC outer sheet from the radius is 14.5 millimeter, which give extra protection from the outside environment. Okay, next is simulation and analysis. In this project, finite element method magnetic FEMM software was used to simulate and study the electric field in the 11 kV 3-core XLPE cable termination. FEMM is an easy-to-use program that can draw and analyze electric field in 2D. It is very useful for high-voltage cable study because it can show how the electric field spread around the cable layer in a clear and detailed way. In this simulation, different voltage were applied to each phase of the cable. For cable A is 6,350 volt, while cable B and C is 3,175 volt. The software is help to show where the electric field is strong and where it is weak. The FEMM simulation display the electric field using color maps and potential line, making it easy to see the high stress area. The main goal was to check whether the electric field inside the cable insulation is safe or is if some part have too much stress. Okay, for the last part of the methodology is a design optimization. The electric field distribution in 11 kV 3-core SLPE cable termination within switchgear by introducing a grounding layer using FEMM software. Initially, a baseline model of the cable termination was simulated to identify high stress region. To mitigate this field concentration, a grounding layer with a relative permittivity of 10 and a surface charge density of 1 exponent negative 10 was added at the termination interface. This layer was grammatically designed to create a gradual transition in the electric field from the conductor to the outer insulation, reducing peak field intensities. Simulation were run using consistent boundary condition and material setting before and after the grinding implementation. The resulting electric field distribution were analyzed through contour plot focused on maximum field stress and strength and stress allocation. The effectiveness of the grinding layer was assessed by comparing peak field value and ensuring the post-optimization result remain below the critical threshold for partial discharge in XLPE insulation. That's all from me. Thank you.
For part A, we began by modeling the 11 kV 3-core XLPE insulated cable using FEMM software. A 2D asymmetric cross-section was created based on standard cable dimension and materials. The model includes layers such as the copper conductor, semiconductive screen, XLPE insulation, lead sheet, and PVC jacket. The core are arranged in triangular layout to mimic realistic conditions used in medium voltage switchgear systems. In part B, we ran the electrostatic simulation using FEMM. The results show that the electric field was strongest near the copper conductor, reaching a peak value of 1.8020 times 10 to the power of 16 Vm. This is due to the sharp voltage drop across a small radial distance. Another area with high stress was at the sheet termination, where the field mixed air. These results highlight areas where stress control is critically needed to avoid partial discharge and insulation breakdown. From this analysis, we identified that the sharp changes in permittivity, such as from copper to XLPE, and the lack of stress grading cause severe electric field concentration. These are high-risk areas for partial discharge, which over time can degrade insulation. This shows that before the cable can be safely used in switchgear, optimization steps are needed to manage the electric field more effectively.
Next, I will explain about task 3 and task 4. So this slide shows the electric field distribution from the FEMM's simulation of a high voltage cable cross-section. The results are visualized using a color density map. The strongest electric field appear right at the boundary between the copper conductor and the SLPE insulation shown in the deep magenta and red, with field value reach up to 1.80 exponent 19. As we move outward through the SLPE, the field intensity gradually decreases, shifting to yellow and orange, indicating a range of 8.44 exponent 15 to 1.33 exponent 60 voltage meter. Beyond this, the film continues to weaken as it passes through the semiconductor layer and outer insulation, shown in the cyan and light blue. Finally, the lowest electric field intensity is observed in the outer air region. So this simulation confirmed that the most critical region for electric stress is at the conductor insulation interface, highlighting the importance of stress control measures in the area, such as grinding layer or semiconductive shield to ensure insulation reliability and prevent breakdown voltage. So next, we'll be discussing about the high electric field at conductor and insulation interface. So this slide highlights two critical regions where the electric field stress is highest in a typical 11 kV 3-core cable. First, at the conductor SLPE interface, a large permittivity mismatch causes the electric field to concentrate near the copper surface. This is further intensive at the SLPE semicon screen boundary due to an even higher epsilon R difference. These areas are highly prone to partial discharge, especially if small air gaps or material imperfections are present. Second, at the outer sheet termination, where insulation ends and the cable is exposed to air, there is a sudden drop in permittivity. This creates a sharp electric field gradient, especially around corner and edge. Without proper field control, such as grinding layer or stress cone, this zone can experience surface discharge and insulation failure under high voltage operation. The third problem identification will be discussed about the partial discharge and insulation degradation. So this slide evaluates the risk of partial discharge and insulation degradation in high voltage cable. Simulation results show that the electric field in a critical area, particularly at the conductor XLPE interface at a sheet termination exceed the safe operation limit for XLPE insulation when the field goes beyond about 4 to 5 kV per millimeter during normal condition, or 8 to 10 kV per meter under overvoltage. Partial discharge can initiate. Partial discharge cause localized damage such as electrical tearing, thermal stress, and formation of void or crack, which over time lead to a decrease in the cable's breakdown voltage. If left uncontrolled, this degradation can compromise insulation reliability and result in complete failure. To minimize this risk, field control techniques such as stress grading layer or geometrical shaping like stress cone are essential, especially area with high electric field concentration. So next I will be explain about task 4, which is design the optimization for this cable. So in this section, we analyze the impact of the graining layer on the electric field distribution along the cable termination region. So this left side is a result before adding the graining layer, while the right side is the result of after adding the graining layer. So before adding the graining layer was applied, the simulation showed a high peak electric field intensity of 1.8020 exponent 16 volt per meter, and after the installation of graining layer, although the peak electric field only reduced slightly to 1.8012 exponent 60 volt per meter, the key improvement was in the uniformity of the electric field. So based on the result we have been obtained from the simulation, before and after at the graining layout will be discussed in detail in the critical analysis, which is before the installation of the adding graining layer. The simulation showed the high peak electric field intensity of 1.8012 exponent 60 volt per meter, particularly around the insulation, air interface, and sheet termination. This region experienced highly concentrated and uneven field distribution, creating localized stress points, such as conditions are known to increase the risk of partial discharge and lead to long-term degradation of the insulation system. After we add the graining layer, it's help redistribute the film more evenly across the termination, minimize stress concentration at the critical points. This more balanced field distribution directly contribute to reduce the risk of insulation failure, enhancing the breakdown voltage margin and ultimately improving the long-term reliability of the cable system. In conclusion, while the numerical reduction appears more, the graining layer clearly fulfills its purpose in optimizing electric field behavior in order to meeting the objective of task 4 and improving insulation performance by reducing the likelihood of partial discharge. So that's all from me. Thank you.
Okay, so for the conclusion of this study is it successfully modeled and analyzed the electric field distribution in 11 kV in 3-core XLPE cable that using FEMM software. By adding a grading layer at the termination, the electric field become more evenly distributed, slightly reducing peak stress and improve the insulation reliability. FEMM also proved to be a useful tool to design and more efficient cable termination in medium voltage system. Okay, also FEMM is good at identify the peak electric field intensity of 1.80 power of 60 at the conductor insulation, which is interfaced with the critical stress zones at the conductor insulation, and we also confirm the field level of exceed the XLPE safe limits, which is 4 to 5 kilovolt per millimeter. Indicate the high partial discharge. Also, this study enhanced the breakdown voltage in terms of their margin and insulation reliability through the better localized stress control. Okay, that's all for this study. Thank you.